G'day. Today I'm here to show you how to use Geoboards to teach maths. Geoboards have traditionally been associated with primary maths, but as the title of my talk suggests, my focus will be on secondary maths. While you cannot in fact do calculus on a Geoboard, there are many topics at the lower secondary level, that is, years 7, 8 and 9, where Geoboards are very useful, and this is what this talk is about. I'm a math teacher, so my talk will be from the teacher's point of view based on my experience. I would like to start with some quotes from this man. He was a famous educator and he liked to give advice to other teachers. The way of teaching is to inspire, not to inform. It is often repeated that, I teach them, but they don't learn. Well, if you know that, stop teaching. Not resign from your job, stop teaching in the way that doesn't reach people. This is Caleb Gatengo, born in Egypt, son of a Spanish trader. He held several doctorates, but he was largely self-taught. He pioneered the use of geoboards and Cuisenaire rods as learning tools. As a mathematics teacher, second language teacher, and a reading teacher, he travelled the world during the 1950s, 60s, 70s, and up until his death in the 1980s, giving seminars and demonstrations. He wrote over 100 books. His most famous publication is called Words in Colour, which is not about mathematics, it's about language learning. But he did write a booklet called Geoboard Geometry, which is on the internet. Gatengo claimed that tools like geoboards and Cuisenaire rods speed up students' learning so they advance way beyond what they would normally learn. And not only that, he said students also retain this knowledge more easily. There is a video on the internet called Mathematics at Your Fingertips, where Gatengo appears to prove this by teaching fractions to a group of grade 1s using Cuisenaire rods. He was very critical of the teaching methods of his day, stating in the 1980s, "There is no good system of learning because we are only concerned with one component, that is, the teacher and what the teacher does, and we give means to the teachers thinking that what the teacher does will make the student do better, and we have not been able to substantiate this hypothesis. What is required is to ask the question, how could I improve the learning?" Gatengo spoke of the subordination of teaching to learning. He studied learning and he believed people have an energy budget for it, and he invented a unit to measure this called an Ogden. He believed people wish to use that budget wisely, but if students are made to memorise things, this is not efficient, and they often forget these things quickly anyhow, which begs the question, did they ever really learn them? Gatengo is said to have invented geoboards, but this needs some clarification, since square lattices have been around for centuries. What is new about Gatengo's approach is that, in my own words, geoboards are not some novelty, and not just a demonstration tool, but a learning tool which you can put in the hands of students, literally, one board for each student, and they can learn about geometry under the guidance of a teacher who gives them repeated, structured exercises. So the idea is to have a class set of about 30 boards. In my geometry class, each student is given a geoboard and a few rubber bands to use. The teacher then sets the students a task, which can be written on the whiteboard if necessary. For example, make a parallelogram of area 9, as in this picture. As you can see, it is very easy for the teacher to correct the students' answers. How did I come to use Geoboards? Well, I looked at a lower secondary maths curriculum, much like this one, and saw a great deal of geometry and graphing. I wanted to make it interesting for my students. When I was a boy, someone had given me a geoboard and told me to make some polygons on it. And this memory had stayed with me. So I decided I would try out teaching with geoboards. I was quite nervous before my first class because I wasn't sure if the students would like them. But to my great relief, they did. Geoboards had passed their first test. They were fun to use. Then it became a question of how many topics I could teach with them. The topics for which I use Geoboards are in red, about 1/3 of them. Note that for some topics, I only use Geoboards as an introduction. I am going to take you on an express tour through all these topics, giving examples of how Geoboards can be used. I will start with the upper primary and go through to the end of Year 9. Here we go. In primary, we normally start with polygons, triangles, quadrilaterals, and other polygons. What can we study about polygons? Well, the name of the shape, which is a rectangle, its perimeter, which is 12 in this case. Does it have lines of symmetry? In this case, it has 2. Its angles, well, to describe them, it's 4 right angles. Its area, which is 4 by 2, which is 8 square units. And its diagonals, which are equal in length, bisect one another, and bisect the area. Another topic on the border between primary and secondary is angles. All the different types of angles, the interior angle sum of a triangle and complementary angles, the interior angle sum of a quadrilateral and supplementary angles, and the interior angle sum of other polygons. Also concave and convex polygons. Next, fractions and decimals. Note that the geoboard I'm using is 7 by 7 nails. Now that gives me 36 small squares. And if we're going to study fractions, 36 is a very good number to work with, because 36 has 9 factors. So I say to the students, let the whole geoboard equal 1. And then I ask the students to make a half, or to make a quarter, or to make a third, or to make 5/12, or 4/9. And there the students are doing equivalent fractions. Also improper fractions. So if the blue is 1, make 4/3. Or 5/2. And for mixed numbers, if this is 1 1/3, then make 2 2/3. Or if that's 2 2/3, make 6 as a triangle. If the trapezium in blue is 3, then make 2 1/2 as a trapezium. And so on. And now we get to ordered pairs and graphs. We are now into secondary maths proper, If I put two rubber bands at right angles, I can form a kind of small Cartesian plane. Now the teacher must then explain the coordinates, the quadrants. It's important the students understand that y equals 1 is a line, not just a point. And the same goes for x equals 2. The next task in this topic is for the students to plot points. So the teacher gives them 3 points and they make a triangle. And again. And again. Now at first the students are very slow, but the more examples you give them, and you can give them many, the faster they get. Still in this topic, we have graphs. The teacher can explain the gradient of a line, rise over run, the y-intercept, and the form y equals mx plus c. And then the students can start to graph linear equations. Y equals x. Y equals 2x plus 1. Y equals 3x minus 3. Y equals negative 6x minus 3. At first the students are very slow. With repeated examples, they get faster. Ratio and percentage. This is an introduction only. But the teacher can ask the students to describe the white area as a ratio and a percentage. Well, as a ratio it's 1 to 3. As a percentage it's 25%. Again, it's 1 to 4 or 20%. And with the different colours here we can make different ratios. The teacher can also ask the students to represent an area as a ratio, in this case 1 to 2 to 3, in different colours. And what's below is a possible answer. Then we have percentage increase and decrease. So, starting with the figure in blue, what is 80%? And what is a 40% decrease? And a 20% increase? And a 25% increase? And a 75% increase? And 80% of the blue figure also as a parallelogram. And 75% of the blue figure also as a trapezium. Congruent triangles. This is just an introduction where the students make some congruent triangles, some right ones, some isosceles ones and some obtuse ones, just to get the idea. Transformations. We have translations, reflections and rotations. And we're back on the Cartesian plane and we start with translations. We make an object. We translate the object back 4 units, or we can translate the object down 4 units, or we can translate the object back 4 units and down 4 units. Reflections. Make an object. Reflect over the y-axis. Reflect over the x-axis. Reflect over x equals 1. Reflect over x equals 2. Reflect over y equals x. Rotations. Make an object. Rotate the object 90 degrees clockwise about the origin. Rotate the object 90 degrees, 180 degrees, 270 degrees, in other words, order 4. Rotate 90 degrees clockwise about one of its vertices, in this case 0, 1. And rotate 90 degrees clockwise about a point inside the object. In this case, the point 1, 1. And now we get to another essential topic in lower secondary maths, Pythagoras' theorem. We can make many right triangles on the geoboard and ask the students what is the length of the hypotenuse. Another example, and another example. Another thing about Pythagoras' theorem is the converse of the theorem. That is, the square of the longest side must equal the sum of the squares of the two shorter sides. If it doesn't, it's not a right triangle. When we test this particular triangle by doing the maths, it's not a right triangle. And nor is this one, despite looking like a right triangle. We can do some proofs of Pythagoras' theorem. This is a geometric proof. This is Euclid's proof. This is an algebraic proof. And this is Garfield's algebraic proof. Parallel lines. Well, this is another introduction. We do two parallel lines and a transversal. And we ask the students, using coins of the same size, to mark the equal angles. And using coins of different size, mark the supplementary angles. Volumes and surface areas of solids. Now we're into Year 9 or M3. We can make a cube on the geoboard and ask the students what is the volume and surface area of the cube. Rectangular prism, the same question. Triangular prism, the same question. A square pyramid with its top removed, and a 10-sided regular pyramid. You can ask the students to make their own three-dimensional shape and then to tell you, as the teacher, what is its volume and surface area. Platonic solids. Well, first the teacher must explain what the Platonic solids are. Now, we can't really make the Platonic solids on the geoboard. Well, we can make one, the cube. But the others, we can't really, but we can attempt to make them. And this is a tetrahedron and its net. A cube and its net. An octahedron and its net. A dodecahedron, which is not nearly right, but it's fun to try and make, as is an icosahedron. The idea is the students will learn the structure by just trying to make these on the geoboard. Next, we look at graphing two equations. The students must name the two equations, and since m1 equals m2, there is no solution, as in this case also. And in this graph, they meet at right angles. So m1 by m2 equals -1, and the solution we see is at -1, 0. And in this case, it's at right angles also, and the solution is at -1, -1. Similarity. This is an introduction only. In 2D similarity, we find the side-to-side ratio, or scale factor, and the area-to-area ratio, or scale factor. In one example, and then another. In 3D similarity, we have three ratios: the side-to-side scale factor, the surface area to surface area scale factor, and the volume to volume scale factor. There are rectangular prisms and triangular prisms. Graphing inequalities. The teacher asks the students to list the inequalities which surround and define the closed area. And there's another example. And there's another example. Trigonometry. We can make many right triangles on the geoboard. We can call one angle theta. Using SOHCAHTOA, the students can express the answer as a ratio, or if they have a calculator, they can find the exact number of degrees of the angle. Another example. They can also find the length of the hypotenuse using SOHCAHTOA and a calculator. The centre of a triangle. This is a topic I would rather teach with a compass and straight edge. However, these can be demonstrated on the geoboard. This is the centroid, which is the intersection of the medians. The circumcenter, which is the intersection of the perpendicular bisectors. The incenter, which is the intersection of the angle bisectors. The orthocenter, which is the intersection of perpendiculars dropped from each angle to their opposite side. And the medial triangle, which is formed when you join the midpoints of a triangle. Lastly, some miscellaneous geometric theorems which can be tried out on the geoboard. We have the triangle midpoint theorem, the angle bisector theorem, Apollonius' theorem, Pick's theorem, and Euclid's orchard. Some conclusions. Why do geoboards work as a learning tool? Well, from the student's point of view, they're fun to use. It's easy to attempt an answer, and it's easy to correct a mistake. Geoboards help one's concentration because attention is totally on the task, as it is with Cuisenaire rods. 3. Concepts are clear and not hard to understand. 4. Integer-based, and that adds to the simplicity. 5. As I mentioned, they can be used to test newly learned geometric theorems and also new polygons or new solids. And 6, they're hands-on, and this helps not just learning but also recall or retention, as Geoboards called it. Why do geoboards work as a learning tool from the teacher's point of view? Well, firstly, students enjoy using geoboards This makes maths class more interesting for the students. Number 2, they cure some students of a fear of maths, and they help other students who find maths just hard or who find maths boring. Number 3, students learn quickly, often advancing way ahead of the curriculum. 4, repeated exercises increase students' skill, understanding, and most importantly, their confidence. Number 5, hands-on learning helps both understanding and retention of knowledge. Number 6, time efficient. Geoboards need only be used for 10 to 15 minutes of a class. In other words, the teacher can come into the class with a set of geoboards, give them out, do 10 to 15 tasks in the next 10 to 15 minutes, then take up the geoboards and give the students a worksheet. Now this is facilitated by the fact that it's so easy for the teacher to correct the answers on the geoboards. And this helps the whole speed of the lesson. Number 7. Once students have done an exercise and they understand it, they can make up their own examples to answer themselves or to ask others. If you put them in groups, this is very easy. Lastly, geoboards are cheap to make, easy to maintain, and a class set can easily be carried in the boot of a car. Geoboard construction. How is this geoboard made? The base is MDF board, though you can also use plywood. It has been lacquered. Black paint is optional. A piece of black vinyl sticker has been placed on one side, and brass nails hammered halfway in. Brass rather than steel nails are better because they are softer to the touch and don't rust. Using an odd number of nails, like 7x7 or 5x5, is better because this gives you a central nail. My choice of 7x7 has enough nails for most activities, while an individual square is not too small, as it is in a 9x9. This is not a commercially made board, but part of a class set I had made myself, quite cheaply, with the help of my students and the local polytechnic. I have a video about this on YouTube called How to Make Geoboards. Some links. Well, here are my links. Math with Geoboards for videos, my website for worksheets, and my email for contact. This presentation will itself be on YouTube or SlideShare. This is a list of videos I have already uploaded to YouTube on lower secondary maths. The two works by Catania that I mentioned, Mathematics at Your Fingertips, and Geoboard Geometry, are both available on the internet. And lastly, Catania put his own approach in a nutshell, saying, "I don't teach, I let them learn."